Hello and welcome to Lecture 31, Math 1B03. In today's lecture, we're going to finish up section 5.3 on diagonalization. So this is actually a continuation of the last lecture. And in fact, in terms of my time, it's the lecture I just gave an hour ago, but depending upon when you last read it or watched it, it could have been a day or two ago. Anyway, what we did in the last class was we looked at when a matrix was diagonalizable. So diagonalizable means that there exists a diagonal matrix D and an invertible matrix P such that A can be written as P times the diagonal matrix times P inverse. And today what we want to do is determine when is a matrix A diagonalizable. Okay, so that's where we're kind of the starting point, and we're going to learn about how to diagonalize a matrix. We did a little bit last lecture. We're going to finish this up in today's lecture. Okay, so let me make myself disappear here and make myself all comfortable to start writing. Okay, so we actually had a particular fact that we used last time, which is that if you have an n by n matrix and you have n distinct eigenvalues, then A is diagonalizable. In a regular year, I would have normally just gave you this example, and it's as good review is to practice finding the diagonalization of a matrix. And I want to just kind of work out another example because this is an important skill to have. So if you want, you might want to pause right now and try to diagonalize the matrix, and then when you're done, come back and then check yourself. Okay, so let's say you want to diagonalize this matrix. Well, you have to find the eigenvalues. And let me just point out that there's a shortcut for this example. Notice that A is triangular. So we already know what the eigenvalues are. They're the diagonal entries. So the diagonal entries are the eigenvalues. So that tells me that lambda equals 1 and minus 1 are my eigenvalues, and I'm happy because they are distinct, so I know how to proceed in this case. Then for each of these particular eigenvalues, you have to find a basis for the eigenspaces. So here I'm doing lambda equals 1, A minus the identity matrix here will give me 0, 0, 6, and minus 2. And I can row reduce this matrix so it has a form 1, negative 1/3, 0, 0. Now this is the coefficient matrix, right? This tells me that x2 is free and x1 is equal to 1/3 x2. And so we can now start writing out our eigenspace here. Well, here maybe I'll write out a couple more details here. So we have that x1, x2 is equal to, and we'll let x2 be equal to t because it's free. So we have t 1/3 t. So this gives me t times 1/3 1. And so now I can write out my eigenspace of lambda equals 1. And let's just say I write it as a span. And so it's the span of the vector 1/3 1. Okay, so we need this information here. We need the basis of the eigenspace corresponding to lambda equals 1. And now we repeat for lambda equals negative 1. So hopefully you tried this out or you're just following along. We put in negative 1 into my matrix. So I got 1 plus 1, so I'm adding 1 down the diagonal. So I get 2, 0, 6, 0, which row reduces to 1, 0, 0. And here I see that x2 is free. And x1 has to be equal to 0. So our solutions all look like x1, x2 all look like 0t, which is equal to t times the vector 0, 1. So this implies that the eigenspace of lambda equals negative 1 is equal to the span of that single vector, 0, 1. And once you have this information, you're actually almost done because now you just have to put the information into the correct place. right? So for the matrix D, you make a diagonal matrix where the diagonal entries are the eigenvalues, and then the matrix P. Make sure let's see if I can get. No, I can't get the information on both. Well, let's see if I can do this. I need the basis element here, and I need the basis element here. And so since one has the eigenvalue has an eigenspace whose basis is 1/3 1, that goes into the first column. And then the eigenbasis for the second one is 0, 1. And so our solution is now going to be A is equal to 1/3 1, 0, 1, and then the diagonal matrix 1, 0, 0, minus 1, and then whatever the inverse of inverse is. So you have P inverse. And normally we don't really care what P inverse is. And just what I want to point out is that you can always check your answer. And here's a quick way to check. You just have to check the AP is equal to PD. If you do this matrix multiplication, you should get the same thing. So this is more just kind of a quick review of how you do this. And I left off actually last lecture with this exact same question. Can we diagonalize a matrix A if it has less than eigenvalues? And it depends. And what does it depend upon? Well, we're going to see that it's going to depend upon the size of the eigenspaces. So we'll make this clear when we come to the second part of today's lecture.